Hi, everyone. Welcome to our first lecture video for Chapter 7. You'll be able to go to the lecture notes in the Week 6 module. So Chapter 7 is all about hypothesis tests, which is testing claims generally about numbers using statistical techniques, specifically in this chapter, normal distributions. The tools of normal distributions that we learn in Chapter 5. Okay, so the most challenging thing about hypothesis tests is matching the language that whoever started developing the idea of hypothesis tests came up with a long, long time ago. And so I'm going to write down a bunch of definitions as we go along. But first, I want to think about what a hypothesis test really is. Suppose you want to convince Dorothy that she isn't in Kansas anymore. So Kansas, at least in the movie, is boring, black and white, just a farm, etc. Oz, on the other hand, is colorful. It has a golden road, and Dorothy wears ruby slippers. How could you convince Dorothy that she isn't in Kansas anymore? Well, I would say, notice that you're wearing ruby slippers. Is it very likely that if you were in Kansas, you'd be wearing ruby red slippers? What is more likely? That somehow in black and white farming Kansas, you found a pair of ruby slippers, or that you aren't in Kansas anymore, in particular, that you are in the land of Oz? That's the question I would pose to Dorothy. I would say, suppose you are in Kansas. Do you really think you'd have ruby slippers on your feet? And I think Dorothy would say, no, that seems pretty unlikely. And so I'd say, isn't it more likely that you aren't in Kansas anymore? And I would expect Dorothy to say, yeah, actually, it might be hard to believe that I'm not in Kansas anymore, but ruby slippers on my feet is enough proof. Ruby slippers are strong evidence that Dorothy is not in Kansas anymore and not in Kansas anymore. I'm saying Canvas a lot because of our Canvas site for the class. Okay, let's take this and let's turn this into a statistical hypothesis test. Suppose someone claims that the average mass of an egg is 50 grams. You collect a sample of eggs, weigh them all, and discover that your sample weighs on average 60 grams. You also know that the variability within your sample, as measured by the standard deviation of the sample, is quite small. Let's say 2 grams to either side. So you ask yourself, if I am living in a world where the average mass of eggs is 50 grams, that's Kansas, is it very likely that I would have a sample, let's do a sample of 35 eggs. 35 eggs where the average mass is 60 grams. That's Oz. Statistically speaking, and we're going to put numbers to what we mean by this, statistically speaking, it is very unlikely that you could collect a sample of 35 eggs that weighs 60 grams in Kansas, i.e., if the true population mean is 50 grams. What is more likely? That you somehow got extremely lucky and found a sample that is randomly much larger on average than the population, or that the claim that the average is 50 grams is just wrong. It's not bad to be wrong, it just is wrong. I think it is more likely that the true population mean is not 50 grams. Okay, that's how you would approach a more statistical hypothesis test where you're using numbers instead of Kansas versus Oz. Someone gives you a claim that the average mass of an egg is 50 grams. Your sample, which is large enough statistically speaking, has an average of 60 grams. You do some statistics and you find out it's extremely unlikely that you could get that sample in a world where the true average is 50 grams. It's more likely that the claim that the average of 50 grams is simply not true. Here we go with some definitions. First definition is called the null hypothesis. This is denoted with H sub 0, although we usually get lazy and just put HO, lowercase o. This is red. H naught. Naught is an old English word for 0. H naught. The null hypothesis is the boring state of the world. It is the claim that you are usually trying to disprove. It is Kansas. Then we have the alternative hypothesis. HA, red, HA. The alternative hypothesis is the interesting state of the world. It is an alternative to the claim that you are trying to find evidence to support. It is Oz. How do you know if you have enough evidence to support the alternative hypothesis and reject the null hypothesis? i.e., how do you know if you're not in Kansas anymore? Well, first off, you have to decide how strong the evidence needs to be. Is it ruby slippers, or a golden road, or flowers? Right? How strong does that evidence need to be? We call this the significance level. Let me bold these definitions. The significance level is often given the Greek letter alpha, which looks like that, or in handwritten, it often looks like a fish, a simple fish like you drew when you were in elementary school. The significance level, let's see, you choose the significance level, which is a probability that is usually close to 0. The classic significance level is 0.05 or alternatively 5%. The significance level says if the evidence I collect would happen only, in this case, 5% of the time or less, then I am confident that my data is strong enough to reject the null hypothesis in favor of the alternative hypothesis. For example, if ruby slippers, waking up with ruby slippers, might happen, I don't know, 0.0001% of days in Kansas. I don't think we're in Kansas anymore. All right. Once you decide your significance level, once you decide how strong your evidence needs to be, then we can collect our data, which is usually in the form of the sample mean, or if we're working with proportions, the sample proportion, and the standard deviation of the sample mean, or the standard deviation of the sample proportion. Now we use this a normal distribution to calculate the probability of observing a sample mean more extreme than our actual data. This is exactly the question we answered in chapter 5. What is the probability of observing a sample mean more extreme than our data? If that, oh yeah, we give that probability a name. That probability is called the p-value. I apologize for all of this lingo. This is not how I would approach statistics, but almost every statistics textbook you're ever going to read is going to say null hypothesis, HO, HA, significance level, or alpha, and the p-value instead of the probability of observing something more extreme than our data. So they're words you're going to need to learn. Now we get to make our decision. Compare the p-value, i.e. the probability of observing a sample mean more extreme than our data, to the significance level, i.e. the probability cutoff under which you would reject the null hypothesis. If the p-value is less than the significance level, then you say that it is extremely unlikely to have observed my data in a world where the null hypothesis is true. So it is more likely that the null hypothesis is false. I reject the null hypothesis in favor of the alternative hypothesis. And that's how we do a hypothesis test. We come up with a null hypothesis. It's usually the boring state of the world. Like eggs weigh an average of 50 grams. We come up with an alternative. Like eggs weigh more than 50 grams on average. That's interesting. You get better omelets, bigger omelets at least. We pick a significance level. Well, if I observe data that would happen less than 5% of the time, I'm going to reject the null hypothesis. We collect our data. Here we go. We collected our data. We had 35 eggs. Sample mean was 60 grams, and the standard deviation was 2 grams. We use that data to figure out what is the probability of observing a sample mean greater than 60 grams. That probability is our p-value. And if that p-value is smaller than the significance level, we say, aha, it's really unlikely that the average mass of an egg is 50 grams. I'm going to reject that hypothesis in favor of my alternative hypothesis. All right, I'm going to do a couple examples. I'm going to use the homework because I want to show you also how to interact with the interface here. Let's see. Nope. Chapter 2. All right, here we go. So question 2, the claim is a banana will last 7 days from the time it is purchased in the store until it's too rotten to eat. What if we hang the banana from the ceiling? Would it take less time or more time to rot? And so we're going to collect 15 bananas. We're going to hang them from the ceiling. And we have all this data here. And so we're going to develop a null hypothesis and an alternative hypothesis. And it looks like our textbook uses H1, not HA. Although I'm probably going to say HA because that's what I'm used to as an alternative hypothesis. All right, so the first question asks, what type of test should we use? We're talking about the mean time it will take to spoil, so we're going to use a t-test for a population mean. Don't worry too much about a t-test versus a z-test. Focus on proportion versus mean. The null hypothesis is the boring state of the world. We think that the average times, we use mu, which is the mean. We think that the mean time is going to be 7 days. And our research question is, does it take less time if the banana is hung from the ceiling? So our alternative hypothesis will say that the mean time is going to be less than 7 days if it's hung from the ceiling. Now, we've picked our significance level. There's that alpha I told you about, 0.01. We have our alpha equals 0.01. Now we're going to use our data to develop a test statistic. So the test statistic, since we're doing a t-test for population mean, is going to be t. And let's hop over to R to figure out the test statistic. Okay, so finding the test statistic or a hypothesis test about a population mean. The first thing to keep in mind is the test statistic is just another word for the z-score, i.e. the number of standard deviations away from the mean. There's some very subtle differences, but essentially that's what it is. So in R, to find the test statistic for a t-test, we use t.test, and we get to put our data directly in here. So I'm going to go our data from this question. This is how I recommend you do it. You can copy and paste that data directly into your R code. You need to put it inside this C parentheses and then paste it. And as long as there are commas between each of the data points and no comma at the end, this data right here will show up no problem. Okay, we're doing a t-test, so we need to put in the data. We need to put in the mean that we are comparing it to. And I think it's mu for the mean that we are comparing it to. And because our hypothesis test said that alternative is that it is less than 7, we need to tell it that we want alternative to be less. Test statistic for t-test where the alternative is less. Run that code. And this is the first time you've really seen a large amount of output from the R code. So it gives you a lot of information here, and you need to know how to pick out the information that's useful. So first of all, it tells you it's a one sample t-test. Good, that's what we wanted. It tells you what the data is, in case you wondered, there's that data. It gives you the t-statistic. Is the t equals numbers. That's the t-statistic. So here, the t-statistic equals negative 1.4264. It tells you about degrees of freedom, which is basically how R calculates that t-statistic. Degrees of freedom is one less than the number of observations. And R actually also gives you the p-value as well, in which in this case is 0.08784. Remember that the p-value is the probability of observing a mean, in this case, less than what your data produced, if in fact the true population mean is, in this case, 7. And what is the mean? Well, the output also shows you the mean. It shows you the mean right there. The sample mean is 6.573. So the t-test code gives you a lot of information. It shows you your data again. It gives you your test statistic. It gives you your p-value, and it gives you the sample mean. And all of that information can go into your homework. So the test statistic is going to be t, which is negative 1.4264. The p-value, oh, and they want to show your answer 3 decimal places, so negative 1.426. The p-value is to 4 decimal places, which is here, 0.0878. That's the number crunching we have to do. Now at this point we say, so 8% of the time, I would expect to see a sample mean at least as small as the one I got. But my cutoff is 1% of the time or less. So that 0.08 is in fact greater than alpha. it's more likely that the true mean is 7 than that the true mean isn't 7. So I cannot reject the null hypothesis. My evidence is not strong enough that the null hypothesis is false. And then we put it all together in an interpretation. The data suggests that the population mean time for the bananas to spoil is not significantly less than 7. So there is not significant evidence to conclude that the population mean time it takes for bananas to spoil if they're hung from the ceiling is less than 7. That is a mouthful. What all this is saying is you didn't see any ruby slippers. So as far as you know, you're still in Kansas. There we go. Let's do one more. Here's one where we don't have data. And so we're going to need to do it a slightly different way in R. So we've got an average of 69 decibels. Okay, so that is, we're talking about a means. So we should do a t-test for a population mean. Will this average increase after the installation of a new computer plug? Well, in the boring world, the average will not increase. They'll stay right there at 69. In the alternative world, the average will increase and it will be bigger than 69. So now we need to compute the test statistic using summary data instead of using raw data. Sorry, I had to pause the video, so that was probably an abrupt transition. Let's get back to it. So our t-statistic, or our test statistic will be a t-statistic because we're talking about the mean. And figuring out the t-statistic when you only have summary data, you have to do this a little differently in R. So I'm going to show you how to do that now. First of all, R runs on what are called packages, which is extra code that other people have written. And you need this package in order to do the test. So when you're doing this using R to find a t-statistic or to conduct a t-test with summary data, you need to use the tsum.test command, which comes from a different package. So you install that package, you read in that package, and then you can do the test. Once you install the package, you don't need to install it again. So let's install that package, and it's already installed, so that's fine. So I require it. And now I put in my information. So we had an average decibel level of 74.6. So the mean.x is 74.6. The standard deviation of that sample was 20. S.x is 20. And we recorded 64 people. So n.x, the number of observations, is 64. And we're testing it against the null hypothesis that it should equal 69. So mu equals 69. Run that code, and it produces the same results. It gives you the data, which now is the summarized values. It gives you a t-statistic of 2.24. So we can copy this 2.24 and put it in for our t-statistic. The p-value is, here it is, 0.02863. And they want it rounded to 3 decimal places. So let's, or sorry, 4. So let's pull that last one off. What was our alpha? It was 0.10. So a probability less than 0.1 means we don't think we're in Kansas anymore. this probability is definitely less than 0.1. Our decibel levels that we recorded, those are ruby slippers. So we do not think we're in Kansas anymore, and we're going to reject the null hypothesis. The data suggests that the population mean has significantly increased. So we're going to reject the null hypothesis. Right? Long answer is, there's our data. Our data is ruby slippers. So we don't think we're in Kansas anymore. And submit the question. What did I get wrong? It didn't like my p-value. Let's take a look again. 0.02863. Let's try it like that and see if it wanted that one. Ah, I see what I did wrong. My apologies. So I put in a p-value as if I had done a test that was two-sided, but we didn't want it two-sided. We wanted the alternative to be more. Greater. And now I get a p-value of 0.0143. So this is maybe a good lesson to remind you that it really matters what your alternative hypothesis is. With a greater than, I wanted to use the alternative to be greater. With a less than, I wanted to use the alternative to be less. And if all I care about is that it's not equal, we use the alternative equals two-sided. And in fact, you can usually just leave it blank and it'll do it for you. So let me put this code in the lecture notes. And I'm going to move it around a little bit so that it's in the right place. Oh, that is in the right place. New, but I need to do a example question. What is this? Four from homework, chapter 7, part 2. And this one is question 2 from homework, chapter 7, part 2. All right, I'm going to pause this video there to give us both a break, and then I'll come back and make a new video talking about 2 other ideas.